Thanks. This is joint work with Itai Avraham, Cyril Gavwal, Anupam Gupta, and Kunal Talwar. So I'll talk about padded decomposition for graphs including a fixed minor. And the main title, you will see where it's coming in a second. So I'll talk about mainly what's the definition of the problem and the basis of the algorithm. I won't have much time, but just to sketch the elements of the analysis. But one thing I do want to show is how do we use a seemingly unrelated problem, which is the cops and robber problem on graphs, to get an algorithm for a completely different problem. Good. So the general problem is as follows. You're given some graph, undirected graph, and the parameter delta, and you want to partition the graph into clusters, which are the diameter of every cluster is bounded by delta. So like small diameter pieces. And the objective is to remove as few edges as possible. There's also a randomized version of this problem in which, again, we want a distribution over partitions this time. In every partition, the clusters have bounded diameter. But now we want that not edges, but every certain sufficiently small ball has a decent probability to be saved, to be fully contained in one cluster rather than being separated into several clusters. So this thing is a very basic algorithmic tool which is useful in many settings. I think originally it was used for distributed computing and for the sparsest cut, multi-commodity and minimum cut problem, gap. But eventually it found many uses. You can see a short list here. In metric embedding, in extension problems, in routing. It's used in really all over the place. Even the modern fast linear system solvers for symmetric diagonally dominant systems. Actually, deep inside there, you can find these partitions. Good. So when we say that we want that the diameter of every cluster is bounded by delta, there's actually two things we could mean. The diameter, one thing you can talk about is weak diameter, where you have the original distances in your graph, and these are the distances in every cluster. The distance as it was in the original graph should be bounded by delta. In a strong diameter, you want to view the cluster as an induced graph, and you want to bound the diameter as on the cluster, on the graph induced on the cluster. So, for instance, in the weak diameter, you can have clusters which are even not connected. But of course, in the strong diameter case, you cannot have. So we're going to talk about the randomized version of the partitions. So this is a slightly heavy definition, but this is the almost only one. So we're talking about what does it mean to be padded decomposition. So forget about this epsilon for a second. Beta is the main parameter here. So decomposition is beta padded if for any point and any sufficiently small gamma, the probability that a small ball, gamma times delta is the diameter bound, the probability that it is cut is at most 1 minus e to the minus beta gamma. And when gamma is sufficiently small, this is roughly beta times gamma. Okay, so we want that for any point and any sufficiently small ball, this ball has a decent chance a small chance to be cut. Yes, and epsilon really means for how large ball we can give any guarantee at all. Usually think of epsilon as some constant. Okay, so just to relate this to the original problem, to the deterministic one, when you talk about number of edges removed, notice that if the graph is unweighted, as we're going to assume in this talk, edges are fully contained in a ball of radius 1. So you need to take your gamma to be 1 over delta. Right? So the probability of an edge being cut is essentially beta over delta. So the average partition when you sample from this distribution is going to cut roughly beta over delta fraction of the edges. Right? So just to put this in perspective, if you look at say the path on n vertices, you must remove 1 every delta edges, right? Just to have you can't have more than consecutive delta edges in a row. So a fraction of 1 over delta is the best you can hope for. And, beta says essentially how many more edges you need to remove. Good. So this is the definition if you still need to stare at it for a second. Some general results that about arbitrary graphs, you can have beta to be logarithmic in the number of vertices, and sometimes you need to pay as much. For certain classes of graphs or metrics, such as doubling metrics or graph with bounded genus, we know better decompositions. Essentially, all these things are tight. They're logarithmic in the relevant parameter. So for this talk, it's not really important to know what is doubling or a bounded genus. The family of graphs we're going to discuss today is the graphs that exclude some fixed minor. So this is a small reminder, what does it mean for a graph to have a minor? So if look at this graph G, you can get a minor out of it by contracting edges and by removing edges and vertices. So H is a minor of G. For instance, this graph, if you keep these 4 vertices, contract all this green path, and delete this part over there, you get a K4, even though you don't have K4 as a subgraph. So K4 is a minor of this graph, and excluding a minor means you can't get H as a minor. Good. So this is a well-known family of graphs, contains, as you probably know, planar graphs, bounded tree-width graph, bounded genus graph. All these graphs are minor-free. So in a seminal paper, Klein, Plotkin, and Rao showed such decomposition. They showed it in the context of the sparse cut problem, which obtained the R square. That was the padding parameter, and the value of epsilon they had was 1 over R. So the algorithm was quite intuitive, but the proof was somewhat, this is a picture from their paper, I think. It's quite complicated. The analysis and slightly the algorithm also was improved by Faccheron-Foll and Talwar to R square. So in this work, we further improve it to order R. And our partition works for a constant epsilon. So this is slightly better. And furthermore, all these results are about a weak diameter partition. We also can obtain strong diameter partition, improving the exponential ones that were known before, and also get strong diameter for graphs which previously we only had weak diameter guarantees, like bounded tree-width and bounded genus, but I'm not going to talk about these things today. I think the main contribution of this work is not that we get R squared to R. This is nice, but not so nice. But that the method that we use is completely different. The method of KPR somewhat inherently has to pay a factor of R. And we hope that using our method, you can actually, we conjecture that log R is the right answer. And through KPR, it seems hard to get. But we hope that through our method, there's a certain thing you have to solve, which will actually give you this optimal padding parameter. And the other nice thing is that it uses a completely unrelated problem, or seemingly unrelated problem, which is the caps and robbers game. So, so now I'm going to describe essentially this game and how we use it in the algorithm to construct this random partition. Everything is clear so far? So Noga nods, but this is no indication, I guess. Good. So what is this game? Again, you have an unweighted graph, and you have a cup, several cups and a robber sitting on vertices of this graph. In each turn, they take alternating turn. In each turn, the cups and the robbers can move across an edge if they want to. The cups win if they catch the robber eventually. But, and this is a full knowledge game. Everybody knows where everybody is located. But the cups win if they can actually catch the robber for any starting point, no matter what. So it's still I think it's not known how many cups you need to catch a robber. It moves between square root and n over something small for general graphs. But for a certain family of graphs, like planar graphs or more generally bounded minor free graphs, we know better than square root n. So the core instance that is useful for a cup and robber game in certain families of graphs is the following insight, that if you fix some shortest path in the graph, essentially you can assign one cup to sort of patrol this shortest path. And he tried to be in a position which sort of face the robber, right? Stand right in front of it, or in the projection of the robber on the path. And eventually, the cap will be sort of in front of the robber and block it from ever reaching this path. If you think about it for a minute, you will see that, like on the plane, if you try to block somebody and stand right in front of them and move along as he moves, eventually he cannot cross the path that you are guarding. And the same thing happens for graphs as well. So Andrea, back in '86, showed how to solve that R-square caps essentially are enough for bounded, for minor-free graphs that, but the size of the minor that you exclude is R. Yeah, so KR minor-free is essentially the largest family. So, let's do it in the pictures. So what are the caps going to do? The robber lies at some place on the graph. So the caps, what they do is build a police station in one vertex. Then they build a police station at some other vertex, doesn't matter which, and have a cap patrol the shortest path between these two stations. And eventually the cap is going to block the robber from crossing this path. And now they build another police station and have two more caps patrol these two shortest paths to the previous stations. And now what happens is that if we're in a planar graph, the robber has to decide, once they block all these three paths, are you in the component that is outside or inside? Right? And you can continue in this manner. Let's say the robber is outside, so you build a station here. You need only two caps, actually. And the key observation that once the robber decided that it is lying in the outside component, the two caps in the middle are not needed anymore. Right? Every time the face is just a triangle, so you need just 5 caps to catch a robber, and you continue in this manner. So essentially, the algorithm it works also for minor-free graphs. You construct a police station in the components that the robber lies in. It's a full knowledge game again. You see where the robber is. You patrol the shortest path to all of the neighboring components. To all of the neighboring supernodes. And what is a supernode? A supernode is the caps that belong to a certain police station. Right? For instance, when we added this police station and these 3 paths, so all these 3 paths and this vertex here, we call this a supernode. And we remove it from the graph. And we look where, because we can remove it because the robber cannot cross this path. So we sort of disconnect the graph into components, and the robber has to decide in which component he lies, and we continue in this manner. And the key observation that if your graph doesn't have a KR, a click on R vertices as a minor, then you don't have too many neighboring supernodes. Because when you contract all the vertices that lie on the supernode, all this shortest path was actually touching all its neighboring supernodes, and the supernodes were touching each other, so you will get a KR minor. So the main thing that we take from this game is, okay, so you can have at most, every such supernode consists of its most R-1 shortest paths, so you need R-square caps in general. Right? But this is not what we will care about for the algorithm. For the algorithm, what we care about is that we have a certain, this algorithm actually gives rise to a certain decomposition. We can call it cap decomposition, which is in some sense similar to a tree decomposition. So every such police station with its patrolling caps will form a supernode of the decomposition, which we put in a certain bag, like a bag of a tree with. Right, and once we have a supernode which partitions the graph into components, we have like 2 children, one for every component. So in one of the components, the outside one, we have this piece. So in the tree, this will be another one of the bags. And this partitions the plane into 3 pieces. So it has 3 children and so on. And the thing here is that instead of having the property that every bug has a small number of vertices, it has a small number of shortest paths. Good. So how are we using this to build padded decomposition. So we need to, what I'm going to do now is show the algorithm for constructing the random partition. So we do this cap decomposition for every component of the graph. We do exactly like the Andreas algorithm. We take some arbitrary vertex, like a police station, build the shortest path to all the neighboring supernodes. Right? And a supernode is all this tree and this shortest path was going to be the new supernode. Apparently, for technical reasons, we need to add a certain buffer chosen randomly around this r-1, at most r-1 shortest path. And this thing with the buffer, the shortest path tree, we call this the new supernode, remove it from the graph, and continue on every connected component. And the skeleton is sort of this shortest path themselves. So graphically, it looks like this. We have the supernode, which is this shortest path, and we add a buffer around it. All right, like this. And how does this gives rise to a partition? So once we have this a cap decomposition, which partitions the graph into these shortest path trees, we look for each one of these trees. And each tree was consisting of some shortest path. So this shortest path is going to be the basis for the clusters of the partition. Right? We take a certain net, a delta over 4 net of each shortest path, and we start to take balls around every point of the net. So to determine the radius of the balls, we pick them according to some truncated exponential distribution. So graphically, if this was, let's look at this shortest path, for instance. We look at it here. We take a certain net. So every delta over 4 vertices, we say, okay, this guy is a center of a cluster. So we have a bunch of vertices, and each one of these vertices, the order doesn't really matter, takes a certain ball around itself and says, okay, this is a cluster. Right? So the first point got this ball. This is one cluster of the partition. The second one also takes a certain radius around it and say this is a cluster, and it could have a different radius. And we do this for every one of the shortest paths, and this gives a partition. So how much time do I have? 10 minutes? Okay, so I guess I'll have time to explain why, what properties of this exponential distribution was using the fact that we had this Kaplan-Rober decomposition. So the exponential distribution has this density, but let's look at a sort of discretized version of this exponential distribution. So when we pick a radius at this range, from delta over 2 to delta, say, so I realize the diameter will be 2 delta rather than delta, so everything must be divided by 2. But never mind that. So a discretized version works as follows. You have some parameter for the exponential distribution. So this parameter b, think about this as the beta, right? It will be more or less the padding that the parameter of the padding that we hope to achieve. So we start at this delta over 2, and each time we toss a fair coin and move by delta over beta over b more if the coin comes up head, and stop if it's tail. And when we stop, we sample from this range. So pictorially, we have some net point here, and we divide this range into intervals of length delta over b. Each time we toss a coin, either to continue to the next interval or stop. And when we stop, we cut somewhere uniformly in this range. So the very useful thing about it, that if you have a ball whose radius is delta over b, so a sufficiently small ball, it should be saved with constant probability. And this is actually what happens, right? Conditioning on the fact that the radius was large enough to just touch the ball, there's a constant probability you're going to toss the coin head a couple of more times and completely save the ball. The only problem is that what happens if the ball actually lies right here at the end? We cannot allow the radius to grow further than delta. So, if we are so unlucky that we tossed all the coins and heads and reached the tail, we must stop here no matter what and cut somewhere in the next range. So this, the cluster formed by this net point, it actually can never save the ball. It can only cut it with some small probability, but it cannot save it. So we say that this net point is actually a threatener to this ball that we want to save, but we cannot save. We can only cut it. And the only concern when you choose the parameter of the exponential distribution, and which immediately gives you the padding parameter you're going to get at the end, is what's the probability you can afford that you reach the tail of this exponential distribution. So clearly it's something like 2 to the minus b. And you need to choose b that the number of net points which threaten any given ball is at most 2 to the b. And it turns out that it suffices to bound the expected number of threateners by 2 to the b. Okay, so just by this vague sketching, you can see that if b is large enough, if b, for instance, was log n, or 2 log n, then in fact you will never reach the tail, right? And you don't have to worry about ever reaching the tail. That's how you get a log n padding parameter for general graphs. But we aim for a much better parameter, so there is some chance of reaching the tail, and we need to bound the expected number of threateners. And this is exactly what the cup decomposition gives us. The cup decomposition, remember, we decomposed the graph into pieces. Every piece consists of at most r shortest path. So even though every shortest path can induce many clusters, only a constant number of them can actually threaten z, right? Because we took delta over 4 nets, only 10 or something like that can be of distance delta to any fixed point z. So it means that every shortest path tree cannot have many threateners to z. So this is very good, only r threateners. Potentially this can even give you a factor which is logarithmic in r, because we can suffer 2 to the b threateners. The only problem is that this is just one shortest path tree, and during the construction you can have many such trees. And actually the technical part of this result is arguing that when you look at a certain point z and a small ball around it, every shortest path tree can have r threateners, but you expect that you will see few such shortest path trees. Intuitively, what's happening is that every shortest path tree that actually threatens z will sort of reduce the distance to z by a certain amount, which is chosen at random. And this is why we choose the random buffers. Right? We had the shortest path tree and took a random buffer around it exactly to be much closer to z. So using some potential function argument, you can show that, which I'm going to skip. That you can show that there are actually expect only an exponential in R rounds in which a certain point is threatened. And again, we hope that there's actually a certain problem which I'll skip, but we hope that you can improve this exponential number to some polynomial in R, which will then give you the optimal logarithmic in R padding. Good. So this is the main open question coming out from this work. I think it's very plausible that you can get a better polynomial bound on the number of threads and solve this problem for minor free graphs. And we hope that this could be useful for other families of graphs. Even a simpler way to start will be to look at graphs of bounded tree widths. We don't know anything better for tree widths that we know for minor free. at least when you care about bounds that do not depend on the number of vertices. Yeah, and a general question is if this cap decomposition useful for anything else. Okay, so thank you.
Just assume that the graph is a good separator.